Welcome to the Sophistic Bridge Design SOFinar. My name is Matthias Singh and today's topic of the SOFinar is the graphically input of a frame bridge, so let me call it an everyday bridge. And we just try to keep our example as simple as possible so that we just can put our focus on the functionality of SSD and SOFI+. And for our twin girder system we are going to use also the CIBD technology, which enables us to design a complex parametric model. But before we will start, little explanation to the functionality of the GoToMeeting software. So you will find a button to display in full screen, and you can type your questions into the box which you may have during the SOFinar. And if you won't get an answer during the SOFinar, you will get the response as soon as possible by email. And we are starting immediately to create a new project. That's why we just go to the SSD 2014. The title of our project will be Sophistic Bridge Design, and the name of the database will be FrameBridge. Then I also would like to choose another directory, and then we just go further to the design code. We're going to use the Eurocode number 2, but without a national annex. But of course you've got the option to take the national annex in the first drop-down menu, where you can choose the national annex by taking the national flag. In the third drop-down menu you can choose the part of the Eurocode which will be road bridges, and then we just also switch from 2D slab to 3D FEA system, which we're going to need for our frame bridge. I would like to choose another drawing unit, so at the moment everything is in meters, or I have to draw everything in meters. And I would prefer taking the unit set so that I can draw my sections in millimeters and the system in meters. And now we just created the database for our project, and now we're just also in the SSD, and at the left side hand you can see the task tree of SSD. And I would like to give you, before we will start with the graphically input in SOFI+, a preview of what we're going to do today. And for that we're just going to implement a new task, and I just need a user text task. And in the user text task you can store additional information for your project. And first of all I would like to rename the user text task. And if I just make a double click on it, I can open the user text task, can write information or additional information for your project, and you also can upload pictures. And I already just prepared a picture of our bridge, what we are going to do today. And now I just upload it to the user text task. So that's what we're going to do today. That's a single span bridge, and you can see that we are also going to create abutments and pilot profiles. And you also can see that we just have here a nice arc, and for the arc we're just going to need the CIBD technology, or we're going to use the CIBD technology. And you can see that we also just have gray areas, and the gray areas are non-effective parts, what we're also going to implement in our cross-section. And then I just confirm the user text task. So we just go further and go to SOFI+ X to start with the graphically input. And we're starting at first to define the geometry axis. And you've got three options to define the geometry axis if you just make a right click on geometry axis. So you can define new axis. You also can create axis from a 3D AutoCAD curve, and you also can import access from another already existing SOFistic database. And what is also important to notice is the difference between structure elements and geometry axes. So we are going to place later on, to use the CRBD technology, we are going to put the structure elements on the geometry axis, and if we just going to change the geometric parameters, the structure elements will automatically change so that we don't have to redefine them again, what I would like to show you later on. First of all, we're just creating a new axis. The name of the axis will be ax_1, and first of all I just have to input a horizontal alignment. So in the first column you can use different types, so you can use straight lines, circular arc, or also transition curve. And if we just choose transition curve, we just have also different subtypes like clotoid or plus curve transition. But to keep our example simple, we are going to use a straight line. And the length of our geometry axis will be 50 meters, and the length of our bridge will be 24 meters. And we are just going to place the bridge in the middle of our geometry axis, so that in case of alterations, I can easily implement additional abutments, for example, at the beginning or the end of the bridge. Okay, now you can see in the AutoCAD window that we just created a geometry axis, and you also can see in the sidebar that we have now different input tasks. So we also have the option to define a vertical alignment, and so we can change the alignment also in elevation. And together it gives me the opportunity to define a truly dimensional curve. But in this example we won't define a vertical alignment. That's why we just go further to the variables. So we just need two variables, one to parameterize the width of the non-effective parts and one to parameterize the height of the cross section. So we are starting with the variable b, which is responsible for the variation of the width of the non-effective parts. And then I just have to create stations. My bridge will start at 10 meters. That's why I just started this first station at 10 meters with a value of 1300 millimeters. What is important to notice is that the sections will be in millimeters, and that's why the values of the variable for my cross section also have to be in millimeters. Then I just created another stations along the length of the geometry axis. And I also just changed the value. And then I just create a new variable, h. And h will be responsible for the variation of the height of the cross section. And we only need 3 stations, so one at the beginning, one at the middle of the bridge, and one at the end of the bridge. The height of the cross section will start with 2000 millimeters. In the middle we would just have a height of 800 millimeters and then 2000 again. And in the third column you can choose between different progression, so you can choose between polygonal, transition left, transition right, transition left plus right, and also spline. For our example we are using the transition left plus right progression. Then we just go to the next task, which is the placement task. And the placements just define important locations along the axis. And we just need 2 placements, one at the beginning and one at the end of the bridge. So at the station number 10 meters and then 34 meters. And at the 4th column you would just have different placements, so you can choose between support axis placement, construction points placements, or also axis at the beginning or the end placements, and also connection point placements. And support axis placements and axis placements will be noticed later on automatically in the definition of the tangent geometry as high points, what we are going to show you in one of our next SOFinar. For our example, we just need support axis placements. And now you can see immediately also that the placements are created. For our model, we also need a secondary axis where we're going to place the twin girders, and I will give you later on more details for the modeling of our system. So we just need 4 secondary axes. One should have a y value of minus 2.25, then plus 0.25, then minus 175, and then plus 175. And you can see in every task that we just have a preview of our input. And every secondary axis will get also a title. And if I just confirm the dialog, you can see also immediately that the secondary axes are created with the main axis name plus their names. So now we're just finished with the defining of the geometry axis. That's why we just go further to the materials and the cross sections. And that we don't lose that much time with the easy and already well-known things, I already prepared the materials and some of the cross sections. So first of all, I would like to delete the default materials because I don't need them anymore. And then I'm just going to import the other materials from my other already prepared database. And now I just can add them easily to my database. Then we just go to the cross sections, and I would like to import some of them also to my database. And now you can see that we also just implemented the sections. So we just have a section for the pipe profiles, which is a circle section. Then we just have a rectangle section for the abutments, and I already prepared one of the twin girders. And I would like to show you how to create the other twin girder. So if you just make a right click, you have just 3 options. So you can create a new standard section, a new solid section, or also new thin wall section. And for our twin girder, we're just going to use the new solid section, reinforced concrete. I would like to give my cross section a name, which will be cross section girder B, and then I'm just going to import the variables from the axis, which will be B and H. And now you can see that we are in the cross-section editor, and in the cross-section editor you can create cross-sections of any shape and any material. We just have to draw the cross-section in millimeters. And that we don't spend that much time with the drawing of the shape of the cross-section, I already prepared the shape of the cross-section in a block. I'm just going to import the shape of the cross-section with the design center of AutoCAD. So that's the design center, and I just have to make a simple click on the block, and then I just can insert the block easily to the cross-section editor. And I also just close the design center again. Now I just place the shape of the cross-section at the origin point. So that's the cross-section, and it's important also to notice that I just placed the shape of the cross-section at the top, so at the origin point. And in SOFistics, distinguishing between eccentric and centric location of an element. And especially in bridge building, the height of the cross-section can vary it. That's why we just use the eccentric location, which is the top of the cross-section. So we are starting at first with the boundary. And if we just make a right click, we just have three options to create boundaries. You can pick lines or curves. You also can draw rectangles or also just make a point and area, which is just in this case the easiest way to create the boundary of our cross section. Okay, then I would like to define the reinforcement, and I just have two options to define reinforcement. You can just draw single bars with the single reinforcement command, or you can also use the line reinforcement command. And if we're just going to use the line reinforcement command, on that line which we just have to draw will be just placed a number of bars, what I'm just going to show you now. So first of all, we're just starting with the line reinforcement on the bottom of the cross section, which will be in the layer number 1, and I'll also just activate the torsional contribution. We're going to use a diameter of 60 millimeters with a number of 5 bars. And then I just have to draw a line, and I just going to pick the lines which are also prepared in the block. And then I just have to do the same thing for the line reinforcement at the top of the cross section, which will be in the layer number 2, and I also just activate the torsional contribution. I also just take a diameter of 60 millimeters with a number of 15. Then we're just going to draw non-effective parts, and we just have two commands. We can use line or diagonal. And I just take the diagonal command, and then I just have to draw rectangles to the cross-section parts where the primary bending shouldn't be. And I also just draw a shear cut. And now we're just coming to the interesting part of the defining of the cross section. We are going to parameterize our master cross section. And with the use of the CRBD technology, it's possible to define only one master cross section. So first of all, you can find the commands in the sidebar to parameterize your cross section, and to keep it simple, we are going to use the Cartesian reference. We are starting with to implement it first, the variation of the height of the cross section. So you can see in our command line what we just have to do. So first of all, we just have to specify the constraint point, and then we have to specify the reference point for the horizontal and then for the vertical distance. And I would like to refer to the origin point, and for that there is a trick. So if you just make a double click on the enter key, you can refer easily to the origin point. And then we're going to parameterize the height of the cross section. That's why we just go to the vertical value, and then we just have to toggle the lock, and then just make another click to change the value. And we just have two options. You can use a variable, or you also can use formulas. And for our example, we are using variables, so we just have to use before the variable or the name of the variable are equal, and after that a hash, and then the name of the variable. And then we just have to do the same thing for the other side, and I can copy the reference easily with the copy command of AutoCAD. And because of the height variation of the cross section, the line reinforcement at the bottom of the cross section also have to move. That's why the distance should be always the same in this example, and so we are using Cartesian references. And I'm just going to refer to the vertex of the bottom of the cross section. And now you can see that the concrete covering of the line reinforcement will be always 50 millimeters along the length of the geometry axis of the bridge. And I also just have to do it for the other side. Then we are just going to parameterize the width of the non-effective parts just with the same command with the Cartesian reference. And I also just refer to the origin point. And now we just have to recognize that we have a negative horizontal value, and that's because of the local system. So everything from the origin point to the right hand side is positive, and everything from the origin point to the left side is negative. That's why we also have to use the variable with a minus before. So it should be equal minus hash b. And then I just have to do the same thing for the other side. And now we're just finished with the defining of the twin girder B, and I just calculated the cross section, a shear center was calculated, and also the center of the gravity. And you can see that we also have rotated principal axis, and I would like to suppress the rotation of the principal axis. Just go to the properties, to the tab analytical parameters, and just suppress the rotation of the principal axis. And now you can see that we just suppress the rotation very easy. And then I just closed the cross-section editor. Okay, now we're just starting with the structure elements. And we're going to place the structure elements on the axis to use the CIBD technology. And we are starting with the twin girders. And for that we just need the line command. And we are starting at the General tab. So twin girder A should be in the group 101. And we are going to use an eccentric beam, and we're starting with A. And we also just changing the maximum edge length along the length of the beam. I'm taking a value of 2 meters. And with a right click on your mouse you just have different options, and to use the CIBD technology it's important to use segment on geometry axis, and then you can place the beam on the secondary axis. And I also just have to do it for the cross-section girder B, which will be in the group 102, and also just with the same settings. I'm placing the beam on the secondary axis B. Okay, so the twin girders will bear the load in longitudinal direction, and I also would like to simulate a flexural and shear capacity. For that we are going to create also our shell element. So the shell element should be in the group 110 with a thickness of 25 centimeters. And I also would like to create a regular mesh, and the alignment of the shell element should be in positive local set. And I also have to implement an orthotropic behavior, because the shell element won't bear any loads in longitudinal direction, it should only transfer the loads in transverse direction. That's why the shell element will have an orthotropic behavior without a membrane and bending stiffness in longitudinal direction, so that we can avoid double stiffness. So we just need a value in local x direction, otherwise we will have numerical problems, and then we just need a value in local y direction of 25 centimeters. And to avoid a double self-weight, we also have to use our concrete, which will be of the material number 5, or I also just turned off the self-weight before what you can do in the properties. And then I'm just going to place the shell element between the other secondary axes. And now we have to connect the twin girders and also the shell element. And so we just need additional lines, and the lines will be placed on the secondary axis C and D, which is also the edge of the shell element. And then I just place them on the other secondary axis. And now I just have to connect them rigidly with the line constraint command. And the line constraint should be in the group 110. And then I just have to pick the lines. And also for the other side. And to control my input, I would like to do an export to SSD. So that's our bridge without supports, and you can see that we just created a nice arc, and also you can see that we also parameterize the width of the non-effective parts. And now we just go back to define the supports of the bridge. And you can create the supports in the cross-member editor. And if we just make a double click on the placements, we just go, and in the cross-member editor, it will be displayed the interpolated cross-section along the length of the geometry axis. And in the cross-member editor, we are going to define the support of the bridge. So we are starting with the abutments, and for that we just need a line. And the abutment should be in the group number 1, or should be in the group number 10. Then we have to define the cross section, which will be a centric beam with the rectangle section. And we also would like to have a maximum edge length of 50 centimeters. And for the braking forces, we need a bedding. And then I just draw the beams. Okay, and now I just have to connect the girders and the abutments. And I'm just going to connect them with a point constraint. And I also define the pipe profiles in the cross-member editor. And I also need point constraints, which will be in the group number 10, with a length of 2 meters and 25 centimeters. And if you would like to change the settings or to modify the structure elements, you will find for each of the commands modify buttons. So I just forgot to put the constraints for the girders and the abutments to define them. I just forgot to define them in a group. That's why I just take the point constraint modify button and just select the constraints, and then I just can modify the constraints again. So the constraints should be also on the group number 10. And then I just draw the pile profile, and the pile profile should be in the group number 1. And I also just use a centric beam and a circle section. And I also need a maximum edge length along the length of the beam of 1 meter. And the beam length is 3.50 meters. And then I just need a point to define also the supports. And now I just can mirror the support to the other side with the mirror command of AutoCAD. And if I just select everything, you can see tiny icons, and you can read that the supports are linked to the placement P1 on the axis AX1. That's just important so that we can use the advantage of the CABD technology. And then I just can copy with base point the supports to the other placement, and copy everything with base point. I can copy the supports to the placement P2. And you also can see, if you just select everything, the icons axis, and you can read also that everything is linked now to the placement P2. And then I just close the crossmember detour. Now I would like to show you the big advantage of the CABD technology. If I just change the geometric parameters, so instead of using a straight line, I use a circle arc with a radius of 50 meters. You can see that I don't have to redefine the structure elements because they just change automatically to the change of the geometric parameters. And now I just use a straight line. And now I just activated the self weight. So I just go to the load case manager and create a new load case where I just activated the self weight. And now I would like to export my system to SSD to see it in the animator. So that's our bridge, and we are just finished. And I would like to just make a linear analysis for the load case number 1. So no errors and warnings, and if I just go to the animator and just activate it, the load case number 1, and you can see that we just have a nice deformation because of the self weight on the bridge. And so we're just finished with the first part, and I would like to say thank you for your attention. I hope you will join us again at the next SOFinar.